was talking to my friend Deepa Lounsbury. We're walking her dogs, and I said, you know, I got to prepare this keynote, and I want to attempt a sort of a high-level, top-down survey of what is it that makes smart grid communications difficult. Can you help me out? And without missing a beat, Deepa says, well, keynotes usually have trends. You need a trend. I said, perfect, that's exactly right, I need a trend. So this is kind of our background trend. The background story is that in the history of electric power systems, it used to be that information was incredibly expensive or unobtainable. Energy started out pretty cheap, and it got even cheaper for a while. And over time, late 20th century, big changes happened. Energy became much more expensive. Information became much cheaper. So this is the reason we're here. Suddenly, there is a reason to micromanage energy where there wasn't a reason before. As information becomes cheaper, there is also an interesting problem, which is that we're having to learn how to use it well. And this actually parallels the change in education, right? It used to be that students sought out a professor because they could uniquely provide them with information. Now it's really a question of making sense of the information, interpreting it, putting it in context. And we have that same challenge here. Because I had so much fun with my trends, there's another trend, which is, you know, the risk that by the time I can finally explain what a smart grid is, people aren't going to want to hear it anymore. But we're still safely, I think, on the left side of that intersection. Luckily, when I don't know what something is, I can search for it on Google. This is good. So I searched for smart grid image search. And there's actually a reason for this, because I think that the entire genre of images, how we depict what we mean by a smart grid, says some interesting things. And I'm going to just show some samples. I don't want to go into details of the particular sources here. There are themes that we're all familiar with, right? We have diversification, new types of resources, more movement to the periphery of the electric grid, interactive loads, different components, a lot more pieces that need to be somehow connected and interactive. Some of these diagrams show you in detail about the how the communication happens, but something that none of them really say is exactly who are the actors, who are the people behind these devices, and when you have the communication links, what exactly is it that's being said, and why are they doing this? You can't really put that in a picture, right? It's hard to encapsulate. And maybe we're not bothering to say this because we assume it's obvious, or maybe we don't know. Sometimes there's a fine line between those two. So let me start with the why problem. In the big picture, why are we doing this? What's the purpose of operating the electric grid? It used to be really that the mission was to deliver a top quality product to anyone, anywhere, anytime. That's how we designed the system. That was the goal. There was a societal mission that we wanted to support productivity and growth. Really being a civilized society meant bringing electricity to everyone, everywhere. In recent decades, that has shifted because rather than necessarily maxing out and doing the best we possibly can do anywhere, anytime, all the time, there's much more pressure to be economically efficient, and it's not economically efficient to do everything all the time, so we're having to think about prioritizing. More is no longer necessarily better. We now think that we may want to produce less electricity rather than more. We certainly want to emit less carbon dioxide. And rather than just providing, really being an instrument for equitable access across society, there's more of a notion of supporting efficient markets. So that means we now have to ask about individual actors because we're no longer all just in the same boat. And of course, there's money as a motivation. I think it's important to remember, well, for consumers, of course, there are other factors than money that motivate decisions, right? It could be convenience or any number of things. Also, I think it's important to remember this sense of responsibility, sense of duty that is, I think, a really important motivator, not just for people who say they're willing to pay more because they're being environmentally responsible, but the utility industry was built on a sense of service, right? In a way that we tend to forget when we're focusing on markets, but when a lineman gets out of bed at 3 in the morning to risk his life to climb up on a pole in a thunderstorm, that's not just about money, right? There are some other values there. Now, we can all agree that we want well-priced electricity. We want to promote environmental goals, right? It's not just the carbon and the other air emissions. In California, we're having a big argument about cooling water use and, running once through cooling units, even though they stabilize the grid. But there are these ecological impacts. We don't want to look at big transmission lines in our backyards. That makes the design more difficult. And of course, we want electricity that's reliable. And what we hope the smart grid will do for us is to make it possible to meet all these objectives simultaneously. Now, I'm being a little facetious here, but sometimes it feels a little bit like this, right? That we're trying to sort of do everything. In fact, the one thing that's not on here is low calorie. The fact of the matter is, it's going to be very difficult to maximize all these objectives simultaneously. In fact, having better technology may make our decisions more difficult because we have more options to choose from, and so we have to negotiate and really talk about, well, how much reliability, for instance, are we willing to pay for? What if we can provide reliability locally? If we can discriminate in the economic sense, right? How much we provide in different ways. There are more trade-offs and hard choices to be made. In the narrower sense, why are we doing this? As we are looking at smart communication systems, we naturally think about, well, what's the purpose specifically? What are we trying to accomplish? And there are very different design choices that would be made based on what is the particular purpose at hand. Is it settlement? Is it operations? Planning? What's the time horizon? Are you thinking about system-wide properties? Are you thinking about individual resources? Are you trying to do an engineering study? And so, for instance, everyone, well, in the general public at least, smart grid, they think smart meters. That's an example of, a system that was designed for the purpose of settlement, primarily. We can also use smart meter data somewhat for operational purposes, but that's not what it was intended for. Had we designed AMI for purposes of operations, we would have done it differently, perhaps. So these stats are, examples for PG&E system. If you were a distribution operator and you had designed the system, you might say, well, never mind putting a meter on every customer. We'll just instrument the important loads and maybe a few strategic places, right? But if you're doing billing, then you have to deal with all the millions of nodes. You might have also said, well, 15-minute data is good, but it's not really what we'd like to see for operations. In particular, as we're getting a lot of these intermittent renewables as distributed resources, we find that, well, we really want to see higher resolution data. This is from San Diego Gas and Electric. It is from a net meter of one large photovoltaic generator with some load. So we don't see how much is being offset here. That's the net power injection. And you can see that on the 1 hour scale, that's kind of a boring graph. The 15-minute data shows some pretty interesting fluctuation. And so Tom Bialik decided that they would instrument and look a little bit more carefully at what is happening there. And it turns out that depending on the time scale that you choose for your instrumentation, you see very different things. So there are the 5-minute data. There are the 1-minute data. So these are all from the same measurements, but he then integrated and represented what you would have seen had you averaged over those intervals. 30-second data, yet more erratic. And if you take 1-second samples, this is what you see. So that is kind of a really important theme with renewables integration because, of course, the variability, the time constants of particularly the solar and wind generation tend to be different than what we're accustomed to. Some of you have seen me present this slide. This is just some of the key aspects of electric grid operation plotted out over a logarithmic timescale to see what are the relevant orders of magnitude of decision-making and information that's of interest. And the remarkable thing is that this picture spans 14 orders of magnitude, right? The conventional analysis that we're sort of most familiar with is on this level of, on the order of an hour. This is where we might do a study of, is there enough solar or wind resource there to fill in the area under a low duration curve, for instance. We have markets, day-ahead markets, hour ahead. As we're bringing in more renewables, that is pushing our time horizon out, certainly in the longer term planning, right? We're trying to make investment decisions now that will get us to where we want to be decades from now with our carbon emission goals. And yet, on the other hand, it's also pushing us out on the small end of the scale because we're having to make decisions on this finer, faster scale, even below the reference there of one AC cycle. So I will say a little bit more about instrumentation and monitoring at this very fine end of the scale. Certainly having inverters, switch controlled devices, and also solid-state devices in transmission systems. You can now essentially take the AC power waveform, chop it up, and reconfigure it. You're making decisions on the very small sub-millisecond timescale. That's becoming an important realm in which to operate. You can draw a similar picture in the distance dimension, not quite 14 orders of magnitude, but still different realms of where decisions have to be made. And I'm going to focus today mostly kind of on this area in distribution systems. But it's all connected, and transmission systems, if you think about, really are the largest man-made artifact on the planet as interconnected technical systems. I say man-made, technically really it was guys mostly who built this. But not just large, but tightly coupled, highly interactive. We always look at United States, North America pictures, right? Let's look at Europe. Wow, it's all really connected, and it's synchronous alternating current. That means effects propagate across this big network. And we now have growing DC links underwater, undersea cables. For how large and interconnected this system is, it's remarkably that it ever operated with as little information as there was. And Todd Laporte, my advisor from actually political science department at Berkeley, had the great line, the grid is an example of a system that works in practice but not in theory. Because we can kind of keep the lights on even if we don't really understand what is happening, or can model the behavior. Right? It seems to be working, so don't touch it. A definition of complexity would be a system that has numerous components that are diverse in all different characteristics. What makes it tricky in the electric power system is that they also belong to different people now who have different interests, and you have this tight coupling. A totally different definition of complexity by Barbara Czarniawska-Jogas is a complex system is one that no single individual can comprehend in its entirety at any one time. And I think this is actually instructive to realize about the electric grid, that no matter how experienced and knowledgeable you are, you cannot grasp the entire thing at once. So again, I want to focus on power distribution systems. In Smart Grid, we talked a lot about the customers who are actually not shown on this picture, and we talk about generation resources. The distribution system is sort of a bit of a mysterious region because it also happens to be the least instrumented and sort of the farthest behind in terms of its maturation, like technologically speaking. There are good reasons for this, right? Because if we want cheap electricity, we don't want utilities to go out and spend money where they don't have to. So just because there's rust on some things, if they're still working, we don't, there have been good reasons for things to lag behind. But as we're trying to now increase the amount of sort of information that's moving and refine the observation and control of these systems, we're having to deal with the fact that a lot of the equipment is quite old. Now, compared to transmission, distribution systems are really actually mathematically much harder to deal with because there's so many variables. No two distribution circuits are the same. A lot of particular local knowledge that goes in. In practice, they're more exposed to the elements, more vulnerable. That's why most of the outages are, the actual outage minutes or hours that customers experience are due to influences in the distribution systems, whether it's squirrels, birds, drunk drivers, trees, what have you. A lot more of that going on. And at the same time, they're really quite opaque to the operators. A kind of a state-of-the-art control room at the California ISO. This is sort of as good as it gets for the system level. There's a lot of data here, a lot of bells and whistles, and a lot of very smart people who've thought about how do you create situational awareness that helps these operators make good decisions when automated systems can't just take care of everything. Some of that is coming to distribution systems, but only slowly, and not that long ago. This is really what you're dealing with in a distribution control center, right, where you have wall maps that are the authoritative reference for which circuit goes where, what's the status of it. You have push pins in the wall, and the telephone was the key. The way that Andy here would talk to the guys in the field who are looking at the actual status of the system. So the ways in which the system was built and operated was founded on the notion that you can't really get detailed information. As a result, it became necessary to do things a certain way, and these are four strategies that I think are very important to recognize that now happen to sometimes push up against what we would like to do with smart grid or automation systems. The first one is, of course, when you don't know what's going to happen, you want to make the thing beefy. You want to give extra capacity both on the generation side, on the transmission side. It's simple. You just size everything a little bit bigger than you might need because you don't know what you might need. Generators were really the only way that AC power systems were even operable is because rotating synchronous machines with steam generation behind it really are so common. I like to call them mom-type generators. They're sort of always there when you need them, and they have extra storage built in. Important to recognize that we're used to thinking of generators with storage because they have storage in the form of a fuel supply behind them, and they have short-term storage that's in the physical rotational inertia, right? It's maybe not a lot of energy, but it's very important for those first few cycles when there's a disturbance. So generators plus storage have really been synonymous with with generators. And it's like mom, because mom has dinner on the table at 7, and if you're late, then there'll be food in the fridge left over, and there's always something to take care of you. Wind farms aren't like that, right? Now, very important in the distribution context is that when you don't know what the state of the system is going to be, the way to really manage that is to simplify things, cut down on the variables, and distribution systems have been designed radially with a strict built-in hierarchy where power flows from the substation outward, out to customers down the circuit. And I have actually some pictures to illustrate that some more. Let me mention the fourth one. When you're not sure what's going to happen, you need an informed human to have the last word and make sure things are safe. That also includes cooperation, right? It used to be that in order to make sure enough generation was provided on the system, somebody would have to pick up the phone and talk to the operator whom they knew at the power plant to say, hey, Joe, can you give us another 50 megawatts? And Joe would say, all right, we'll try. Everybody was on the same team. And that sort of cooperation is not something that we factor into the market economy, right? But it's sort of what you needed to make it work. So on the radial distribution, there's two reasons that's important. Primarily, it's because of safety for protection systems, right? And this is why distribution operators get really a little queasy about having a lot of distributed generation with a feeding power that's going to flow in reverse, because the coordination between these circuit breakers, reclosers, fuses, all these different protective devices may get confused, and it's important that these each actuate when there's a fault or some dangerous situation, and that the right one actuates. Now, it's possible to redesign protection systems to accommodate two-way power flow, but it's a lot of money to do that, right? Another aspect of the hierarchical design is voltage, which classically has this, monotonically decreasing voltage from the substation down, and the legacy equipment is assuming this in order to control voltage properly. And we don't want the voltage to be too high because it's going to fry people's equipment. We don't want it to be too low because, well, the light bulbs will be dim, and some equipment, again, might not, and especially motors, don't like voltage too low. The irony is that a lot of utilities actually don't really know whether they're within this range because there's no monitoring that tells them. And it's sort of a don't ask, don't tell kind of situation, right? Because as long as customers don't call to complain, nothing's breaking. Curiously, counter to stereotype, in Germany, the permissible range is plus or minus 10%, which I'm actually not sure if that's because their appliances are better made so that they can tolerate the bigger voltage variations, or exactly why that is. It's something to look into. Anyhow, the point about operator discretion is really that there's any number of ways people can get killed in distribution systems. It's a little bit different than in transmission, where many millions of dollars are at stake. So transmission operators don't want to make mistakes because they could be costing the company a whole lot of money and see, the disaster blackout in the paper the next day. So there's a strong incentive to not do stupid things. In distribution systems, it's a much more immediate sense of people can get killed. And when I was a graduate student and I interviewed distribution operators about what they do and explained to me how this thing works, there was not a single shift of operators that I talked to where at least one person hadn't been directly familiar with an incident where, somebody got electrocuted, some guy got killed, a guy had his ear burned off by a 12 kV, and how it smelled when that happened. I mean, their worst nightmare is that they're going to initiate a switching procedure of reconfiguring circuits, and there's a minivan with kids in it that's under that energized line, and by actuating that switch, they're going to kill them, right? So this is why there's such a strong sense in in the industry about retaining control and not letting scary things happen, because there is that very visceral sense of understanding the physical dangers. So here comes the smart grid, right? And now we want to be economically efficient. We want to have inverter-based generation, which is very good, but it's not the same as MOM, right? In particular, distributed generation is scary because it can subvert this whole radial hierarchical paradigm. And now we have active participation by a lot of different customers' resources at the periphery who may be challenging the operator's exclusive control. So it used to be simple. There were basically utilities and customers. Now there's a whole lot of other parties to think about. There's issues about who can find out what, or who even cares about what, who has the last word on control. And what interests me in particular is this notion of the grid as a commons, because in many ways it is a sort of a common resource. And just to give one example, you could think of a voltage profile as sort of a commons. I'm sorry I didn't reference one of the graphics. Did any one of you make this graphic? It's just an example of, one way to think about, you have many different devices now on distribution circuits that can participate to regulate voltage. I mean, it's really a piece of cake for an inverter to do whatever you ask it to do to stabilize voltage, pretty much. Produce this many bars, hold a voltage set point. The trick is figuring out what to tell it to do. It's easy to say, well, all right, we'll have an algorithm that does all that. Some of my incredibly smart graduate students can probably write an algorithm that optimizes for one of a number of objectives. What they can't do is decide for everybody which of these objectives is more important, right? Because it's not, what do you want to do with voltage optimization? What's optimal? Do you want to avoid customer complaints? Do you want to do conservation voltage reduction? Do you want to minimize losses? What about the trade-off of how much money a generator could get paid if they weren't regulating voltage? What about legacy devices wearing out because they have electromechanical controls that were designed to operate a couple times a day, not every time the cloud passes over the solar panels, as you saw in the picture? And another interesting one to me is that not every voltage profile is consistent with every switching reconfiguration options, right? So a concern for operators is whether they're going to foreclose certain options about feeding a certain section, for instance, from an alternate direction, because then the voltage profile isn't going to add up. So there's a lot of different choices. What I'm tempted to say is, well, let's just put all the information out there. What if, so there's me with my iPhone saying, all right, what's traffic on the streets right now? What if I could look on my phone and see, well, what's the voltage on the feeder right now, right? No reason technically you couldn't do this, right? I mean, is the business case there for it? I don't know. But I think this is actually an interesting thing to think about. Now, what we have in the real world is we have maps of just where the feeders are. So this is, again, in my neighborhood. So we can see for purposes of siting distributed solar, there's maps online of what's the connectivity of distribution circuits coming from the substation. That's pretty cool. Going a whole different direction, P-Cubes, a power quality instrument made by Power Standards Lab. Different people have them plugged in different places in the world, and they communicate in real time. This one happens to be in Shanghai. Communicate voltage, current, power quality. All right, this one is in California. We're seeing low voltage sag. I purposely didn't pick really interesting graphs because I didn't want to spend too much time on it. But you can go to the maps.pcube.com and browse and look at, well, what's happening on the grid, elsewhere in the world. interesting post-mortem analyses, right, you could do to see what happened before big outages, or for instance, what happened in Japan as they were trying to manage the grid after the tsunami. Here's a completely different approach, or maybe not. This is slide courtesy of Jason Bank at NREL. Getting pretty close to this fantasy of seeing real-time conditions on the distribution feeder, not on your iPhone, but actually, well, it's on the internet. So this is a project that NREL is doing with the Sacramento Municipal Utility District, SMUD, and they're getting live data feeds. One thing that I love about this visualization is that he's got the 3 phases, A, B, and C, color-coded with the yellow, orange, and brown. And then they've got different symbols for where they have storage units, where they have rooftop solar. And then you can zoom in and you can see the generation and voltage levels at these particular locations. So this is pretty cool. You can get to it if you have proper credentials, and I'm jealous because I can't see this on my phone. So this this example raises this question, ultimately, who should be able to have access, right, to this real-time information? Are there security and privacy concerns that really are prohibitive for making this kind of information public? Now let me sort of go on to this question of what are the physical variables, or what is the concrete information, what are the instructions that one might actually want to communicate. So there might be things I haven't thought about, but really taking the big picture view, we started out with mostly energy kilowatt hours and power flows at some of the critical nodes in the transmission system and certainly at the generators. And control for generators pretty much amounts to instructions on power or instructions to maintain a particular voltage level that's related to reactive power Q. Now, any of these variables in principle you can observe and you could control from distributed resources, and there's sort of this big field of possibilities, and the question, well, which is the right variable, right? We often assume that the unit in which we communicate is price, right? Particularly with customers, that customers respond to price signals. And of course, you have to think about what is the motivation. Ultimately, there has to be some financial incentive. But as your control variable, you could pick physical measures, such as voltage or voltage angle. I'm a big fan of delta, the voltage angle. And so I want to tell you a little bit about a research project we're doing that involves really focusing on voltage angle and seeing what we might do at the distribution level using angle as a state variable. Down the road, a control variable perhaps, but we want to start with just making diagnosis of system conditions based on angle. If you're not a power engineer, here is sort of the basic 101 on voltage phase angle. We speak of synchronous AC systems. That's actually not exactly true, right? Because in order to have AC power flow, the laws of physics actually require a tiny little shift in the timing of the voltage sine wave. And that corresponds to how much real power is being pushed through a transmission line. So if I have one generator that's pushing harder than another, physically, that means the voltage waveform at that generator is going to be a little bit ahead in time by this amount. We never were able to empirically measure this. We could write equations, but in order to measure this, you need to have a common time reference, and they're very small time differences, right? Because you might be talking about a few degrees, where 360 degrees is 1/60th of a second, or 1/50th. So it took GPS, satellite communication timestamping, to be able to even empirically observe that voltage angle difference. In the last couple of decades, this has become an immensely valuable tool for transmission operators because they can now see a kind of an MRI of power flow on the grid. And I'm actually curious, well, maybe somebody besides system operators could look at this information. But just one example is in '96, there was a big outage on the West Coast, and nobody kind of understood why until a very early synchrophaser, a set of synchrophasers that were actually measuring voltage angle differences across the California-Oregon intertide here, were able to pick up these oscillations in the delta, these oscillations that were obviously underdamped and then resulted in relays tripping, transmission lines opening up, big blackout, that according to our models and predictions and simulations came completely out of nowhere, right? So the synchrophaser technology is a way to really see, are you swimming with sharks? What is going on in terms of oscillations or instabilities? Now we just got funded by ARPA-E with UC Berkeley, Lawrence Berkeley Lab, and Power Standards Lab to explore the use of synchrophasers or PMUs, phasor measurement units, but the micro version for distribution circuits. And if you look at this diagram carefully, you might notice that once again, it doesn't tell you who says what to whom, right? But you have to go pretty deep into our proposal to figure out that we're actually not entirely sure who's going to say what to whom, because it's difficult, right? It's even harder than figuring out how you're going to say it. There's actually a long list of possible applications that I'm not going to go through. I just want to tell you a few things about the devices based on the P-Cube that I showed you with its online uploading, which ultimately you could see, well, yeah, you could have voltage angle accessible. The key thing for making this work in distribution systems is making it affordable, but also you're going to have to measure much smaller deltas on distribution systems because they're smaller power flows. So it needs to be a very high resolution device. Also to make sense of the data, you're going to have to put it into context with power quality measurements. That's why there's a lot of samples per cycle. And we're actually struggling with the math right now about the conflicting requirements of phase lock sampling for power quality and time-based sampling for synchronized measurements. Those wouldn't be any different if only the frequency could just stay at 60.00000 hertz, but it won't, right? And we're trying, so interesting problems of math and physics that you get into when you try to take such a refined look at the small end of the time scale. The problem with who says what to whom and why is, well, what exactly we're going to report there on the measurements are going to depend on what you're going to do with it. Different kinds of applications are going to have different requirements for resolution, time stamping, also spatial density, where you place the devices, and what we expect of the communication network. Can we tolerate a certain amount of latency? Can we tolerate interruptions, and so forth? The device itself is capable of taking a lot of measurements, but the question, as always, is, well, how much of that is worth pushing out? How much of that is worth communicating? And for research purposes, of course, we want to start out with a kind of a fire hose mode and say, well, let's just look at everything and see what there is, and then we'll begin to make some sense of it. That really is, one of several strategies when you don't know what exactly you're going to need. You sort of have three choices, right? You can build the infrastructure based on your best guess of what it has to do. You can wait a while and study the situation more carefully so that you can have a better informed guess of what it's going to have to do. Or you can say, well, we don't know, let's just prepare for all possibilities. And each strategy has some risks, right? The risk in the first case is that you don't get what you really wanted. In the second case, you might wait around a long time and then find that really to know what you want to do, you have to just do it. You have to learn by trial and error. And in the third case, if we say, well, we just grab all the information, put it out there, that may be a lot of initial investment. And in particular, with distribution system data, there is this question of how do you account for privacy and security needs, what may be the constraints on that. As I was writing this down, it sort of occurred to me, where have I experienced this trilemma before? And of course, this is what you always go through when you're packing for a climb. I don't know if any of you are climbers, but there's, you know, this question, you're going to do a route you've never climbed before, what gear do you bring, right? I mean, do you just make a guess and you take it along? You might be wrong and you'll be sorry. Or you study the book very carefully and talk to everyone you can and try to make a very informed selection. Or you say, well, I mean, in some cases, if it's a first ascent, nobody will know. So you just bring everything you can and suffer the weight of the pack as you go, right? So I don't have conclusions because it's not an argument I'm making, but there are takeaways, observations here. One is that it behooves us to remember just how profound a transformation the electric grid is undergoing. And there are reasons for people to have done things a certain way in the past that sometimes don't mesh well with some of the more refined strategies one wants to implement. And there's a lot of possibilities, a lot of combinations of who might say what to whom and why. And we can go ahead and make assumptions about that. And the more we assume, the smarter we're going to sound, because it'll sound like we know what's happening, but in fact we should be aware that there may be other options. There are conflicting and also common interests. I think it's important to remember that in the end, this infrastructure is one that's, because it's so tightly coupled, it really links so many of our interests in a way that it behooves us to appreciate it as a commons and think about how can we motivate this sort of constructive behavior toward supporting a common. It's a kind of a citizenship. Finally, you know, what options become open if we don't imagine information as being constrained, like it was for many of the early decades of the power industry. I'll be happy to have some questions.